Hello, Dan here from howtomechatronics.com, and in this video we will find out what's better, a 3D printed harmonic drive or a 3D printed cycloidal drive. Here I have these two gearboxes that I made which have the same size and reduction ratio of 25:1. I will compare them in several categories, measure their efficiency or torque output, measure their accuracy or backlash, and see how durable they are. I will explain how I designed and assembled both of them, and I will give you some useful tips and tricks for 3D printing them, show you what can go wrong and what can we improve to get them better, things that I've learned along the way of making several of these. Actually, this is my fourth video talking about these gearboxes, and why so? Well, these gearboxes are a good choice for robotics applications, and in future video I plan to make some robots that will employ this type of gearboxes. I already have dedicated videos on my channel explaining in details what are and how harmonic and cycloidal drives work, as well as how to design them, so I would suggest checking those videos out for more details. Real quick, both the harmonic and the cycloidal drives are unique type of gearboxes, or speed reducers, that provide very high reduction ratio with compact but robust design. Their working principle is kind of similar, where their input shaft drives a non-regular shaped part, a wave generator in the case of the harmonic drive, and an eccentric bearing in the case of the cycloidal drive. Then, with the help of some more unique parts each gearbox has, they are able to generate output with significantly lower speeds in a very small space. The reduction ratio of the harmonic drive is always half the number of the flex spline teeth. If we want 25:1 reduction ratio, we need 50 teeth on the flex spline and 52 teeth on the circular spline. On the other hand, the reduction ratio of the cycloidal drive is always one less than the number of pins on the ring gear, or for 25:1 reduction ratio, we need 26 pins on the ring gear. Again, as I mentioned, you can check my dedicated videos for detailed explanation how these drives work. Okay, so now let me show you how I designed the two gearboxes for this video. So my goal was to make them the same size and have the same reduction ratio so that I can easily compare them head to head. I wanted to have 25:1 reduction ratio and make the gearboxes as small as possible. The base and first input parameter when designing these gearboxes was the size of the pins that I had for the rollers for the cycloidal drive ring gear. I had 6mm pins which I planned to put them in 8mm bushings in order to get smoother operation. So I draw a sketch with 26 rollers and bushings with 8mm diameter. Now, according to these two input parameters, I could define the minimum size of the ring gear pitch diameter, which eventually defines the size of the gearbox. The housing diameter had to be 95mm in order to fit all 26 bushings and have enough wall thickness for some M4 bolts for assembling the whole gearbox. For generating the cycloidal disc shape, we need one more input parameter, and that's the eccentricity value, which should be smaller than half of the pin diameter. For drawing the unique shape of the disc, we can use the following parametric equations, which can be found in a document written by Omar Yunis for the SolidWorks education blog. Now I will show you how I used these parametric equations for making the cycloidal discs using SolidWorks and its equation-driven curve tool. It's worth noting here that these industry-leading and professional-grade design tools are now available to all makers at a remarkably low price of only $99 per year or $9.99 per month. That's right, 3D Experience SolidWorks for makers is great for anyone learning the trade, making DIY projects and more. This offer includes 3D Experience SolidWorks Professional, the most in-demand CAD tool within the offer, and runs locally on your PC. You can store files locally or in the cloud with the 3D Experience platform. Xdesign, browser-based CAD, you can use it with 3D Experience SolidWorks or on its own. It's great for modeling anywhere, anytime and on any device. Xshape, browser-based freeform CAD that's easy to use for surface modeling on any device. Visualize Connected, easily create photo quality images, animations, interactive web content and more to impress your audience. As well as NC Shop Floor Programmer, CAM for intelligent machining strategies for 3-axis milling, and Wire EDM in an easy-to-use package. So click the link in the description below and you will get a special 20% off, so you can start making with the best today. Big thanks to SolidWorks for sponsoring and supporting educational content like this. Back to topic, we can easily generate the cycloidal disc shape by inserting the two parametric equations in place. Of course, we should use our parameters in the equations appropriately. As for the t parameters, we should use values from 0 to 2 pi. Though we should note that we need to use slightly smaller value than 2 pi in order the curve to be generated. This will generate the curve with a little gap which can be easily connected with a spline. Then we can simply extrude the profile and make the holes for the eccentric bearing and the output pins. So the cycloidal discs along with the eccentric bearing and the ring gear rollers are the most important parts of the gearbox, as the rest of the parts are designed around them. The design of the gearbox depends on many factors such as motor type, how we would like to drive the input shaft, what kind of bearings we have available to work with, the application of the gearbox itself, and so on. Nevertheless, let's take a look at the harmonic drive now. As I mentioned, the idea was both gearboxes to have the same size, which I was able to get it in terms of gearbox diameter, but the length had to be a bit longer in order to accommodate the flex spline. Here we have the flex spline, which is a very unique part because it has to be flexible at the open end but rigid at the bottom or the output. If we try to make the cup shorter in order to match the length dimension of the cycloidal gearbox, it won't work properly as we are using PLA material which doesn't have enough flexibility and its thin wall would easily break. For designing the flex spline, I used the SolidWorks toolbox to generate a spark gear with 50 teeth. I chose a module of 1.5 which gave me a dimension suitable to match with the cycloidal gearbox. I saved it as a separate part file and then started modifying it. I made the wall of the cup to be 1.25 mm and the total length of the cup 30 mm. As for the circular spline, I used the same method. With the SolidWorks toolbox I generated an internal spark gear with 52 teeth this time and then modified it according to the rest of the gearbox design. I made a slight clearance or offset of 0.1 mm inside the gear, just to make sure that the gears will mesh properly, because it's a bit hard to get very accurate 3D printed parts. Then for the third key component of the harmonic drive, the wave generator, I drew an ellipse with the major axis 3.2 mm larger than the inner wall diameter of the flex spline, minor axis 3.2 mm smaller. Now according to this ellipse I arranged 3 bearings at each side of the major axis in order to achieve a smoother deformation of the flex spline. The rest of the harmonic drive was designed according to these 3 key components. You can find and download both the harmonic and the cycloidal drive 3D model and the STL files needed for 3D printing on the website article. The link is in the video description. When 3D printing, in order to get accurate dimensions of the parts, we need to have proper settings in our slicing software. The most important settings for getting dimensionally accurate prints are the horizontal expansion and hole horizontal expansion settings. If we leave these settings by default, the print's outer dimensions as well as the holes are usually smaller than the original model. In my case, I set the horizontal expansion to 0.02 mm and the hole horizontal expansion to 0.04 mm. Of course, you should do some test prints to see what values will give you the best result on your 3D printer. Though for some of the parts I used different values for these settings. For example, for the flex spline and the cycloidal discs, I used a value of -0.02 mm for the horizontal expansion setting. This way we will be sure that the prints will be definitely smaller than the original, as these parts must have clearance fit to be able to move. Okay, so here I have all of the parts ready and I moved on with assembling the gearboxes. I will include a complete list of components needed for assembling them, like bearings and bolts, on the website article. In order not to overload the video, I will walk you through this assembling process a bit quicker than usual. I will just point out the important aspects of it. When assembling the cycloidal drive, the most crucial thing is to make sure that we place the two cycloidal discs 180 degrees out of phase. I made a small hole on the disc which can help us with that. We should position the holes 180 degrees apart, or if we flip the discs, we can just align the two holes and that will get us the 180 degrees out of phase positioning. Here's how the two cycloidal discs in combination with the output shaft look when assembled. On the eccentric shaft we can attach and secure any input shaft coupler using the 3 M3 bolts. In this case I placed one for a NEMA23 stepper motor. Though we can note here that fastening these bolts can be a bit messy, because the holes on the eccentric shaft are small, so that the bolts can make thread into them and have tight fit to avoid any backlash from here. It's probably not the best solution, but it will work. Once we place this sub-assembly into the gearbox, we can see the magic of the cycloidal drive and how it works. At this point it seems that it works quite smoothly. When inserting the lid in place, we should make sure that we align the bushings with the pins, as well as align the 6 holes that are used for securing them in place. Lastly, we can attach the NEMA23 stepper motor with the help of this mounting bracket. Of course, we can change the input shaft coupler and the mounting bracket to fit any other motor. And here it is in action. Just take a look how smooth it works. The output shaft rotates 25 times slower than the input shaft in the opposite direction. Okay, so next is the harmonic drive. The harmonic drive assembly is a bit quicker as it has less parts compared to the cycloidal drive. The output shaft is secured to the flex spline, which is then inserted into the circular spline. The wave generator is composed of 2 sections, which should be secured together with 4 M3 bolts. I designed it this way so that it has support on both sides of the gearbox with bearings. The wave generator bearings that will roll on the inside and deform the flex spline are with 6 mm inner and 13 mm outer diameter. I secured them in place using some M3 countersunk bolts and some M4 washers. The reason for that is to save on space as much as possible. Then I inserted the wave generator into the flex spline with a little bit of squeezing. Actually, it's much easier to first put the wave generator into the flex spline and then put those two into the circular spline. And here's the harmonic drive magic as well. We can see how cool it works, although the movement is a bit jerky now, and we will see why a bit later. I applied some lubrication to the gear meshing, which improved the motion a little bit. The gearbox housing is completed with inserting the lid at the back side and securing it with 6 M4 bolts. Then we just have to attach the input shaft coupler that we want, and in this case that's again for a NEMA23 stepper motor. Lastly, I attached and secured the NEMA23 stepper motor with the mounting bracket, and with that the harmonic drive was completed. So here it is. The output shaft rotates 25 times slower than the input shaft and in the opposite direction. But compared to the cycloidal disc, the motion doesn't seem to be that smooth. There are several reasons for that, and now I will show you them. The first reason is that the flex spline was actually already broken. The cup wall is just too thin to withstand that amount of deformation. The problem here is not just that the wall is too thin, but also the fact that the cup is too small in order to accept that kind of deformation. If the cup was a bit bigger, which was the case in the design from my other harmonic drive video, it would be able to elastically deform much better. The length of the flex spline is even more important in order to get better results. However, here I was trying to make the two gearboxes to have the same size, so I kept trying to get it working like this. I tried 3D printing it with another filament and with increased wall thickness of 3 lines this time, but it failed quickly again. The second problem was that the wave generator was not making the right contact with the flex spline. We can notice here how the top bearing is not touching the flex spline at all, only the 2 other bearings were making contact. So I modified the wave generator to only have 1 bearing, and that improved the motion. Another thing that was causing problem was that the inside surface of the flex spline, where the bearing was in contact, was not that smooth. That's because of the thin wall, and because when 3D printing, only 1 wall line was passing behind the teeth of the flex spline, and the surface was not smooth because of that. By increasing the wall thickness to accommodate 1 more wall line when 3D printing, the surface got much smoother. So here I'm using wall thickness of 4 lines or 1.6 mm thickness of the wall, and the motion was improved. However, there was one more problem. In my slicing software for the Z-Sim alignment I was using user specified, which meant that the starting point of each pad was at the same location, and that was causing the part to have one more noticeable bump on the surface. In order to avoid this, I set the Z-seam alignment to random and I got a smoother surface and better motion. Alright, so now let's see how the two gearboxes compare to each other in terms of accuracy, efficiency and durability. Here on the left side is the harmonic drive and on the right side is the cycloidal drive. The repeatability of the cycloidal drive is quite good, but once we apply a load, we can see how much backlash it has. At a distance of 15 cm, when applied force in both directions, there was around 6.5 mm play. On the other hand, the harmonic drive had the same good repeatability as the cycloidal drive. However, when force applied in both directions, it showed a greater backlash, with 8 mm play at a distance of 15 cm. If we observe the backlash in still position with applying just a little bit of force, then the harmonic drive was showing kind of better results. Here it felt like even there is no backlash at all, because even with the slightest touch, the output was giving some resistance. On the other hand, on the cycloidal drive there was around 2 mm of totally free play on the output, at the same distance of 15 cm. However, when applied a bit larger force, the cycloidal drive showed slightly better results, or 5.5 mm play, whereas the harmonic drive showed up to 7 mm of play. Let's take a look at the torque outputs now. Here's the first try of the cycloidal drive and bang! 22 newtons at a distance of 15 cm and something just broke. I took the lid out to check out and that was the output shaft that broke. I printed a new one in white PLA now and with higher infill density and higher temperature to get the part stronger. So with the next run nothing broke and it maxed out at 32 newtons at a distance of 15 cm, or that's a torque of 4.8 Newton meters. Compare that to the torque this NEMA23 stepper motor provides without the gearbox, around 2 newtons at a distance of 15 cm, or 0.3 newtons of torque. That's increase of torque of around 16 times. That's efficiency of around 65%, as the reduction ratio is 25:1, and in ideal condition we should get 25 times torque increase, but we only got 16 times increase. The harmonic drive gave exactly the same result of 32 newtons at a distance of 15 cm, or 4.8 Newton meters of torque. Again, that's the same efficiency of around 65%. To me that was a bit of a surprise, as I expected the harmonic drive to be even less efficient than the cycloidal drive. So as the NEMA17 maxed out at 4.8 Newton meters, I replaced it with one big NEMA23 stepper motor by changing the input shaft and the mounting bracket. This thing alone has a torque of 3 Newton meters. I initially tried testing it with the same 15 cm wooden stick, but it simply broke at 80 newtons, or 12 Newton meters of torque. I replaced it with a stronger plywood stick and measured a force of 30 newtons at a distance of 50 centimeters. That's a torque of 15 Newton meters, which is only 5 times higher than the 3 Newton meters the stepper itself was producing. Here it was not the stepper motor that was maxed out, but the cycloidal drive started skipping. A look inside revealed that the cycloidal discs broke in the area where they are in contact with the eccentric bearing. I 3D printed new discs with 4 wall lines and increased infill density and put it to test again. Now the cycloidal drive reached 43 newtons of force at a distance of 50 centimeters, or that's a payload of around 4.4 kg at a distance of half meter, or 21.5 Newton meters of torque. The gearbox started skipping again and a ton of backlash appeared, which meant that there was another failure in it again. A look inside revealed a deformation of the shape of the cycloidal discs. So I guess that would be the maximum torque this driver can handle. Although that's just 7 times torque increase, I think still it's quite impressive, as these are really big loads, considering this is just 3D printed and such a small gearbox. On the other hand, the harmonic drive failed right away with the NEMA23 stepper motor. There is simply no way the harmonic drive can handle that amount of torque as the cycloidal drive. The flex spline wall is just too thin and the PLA material too weak. In terms of durability, it's the same thing. The cycloidal drive can last much longer than the harmonic drive. Of course, we are talking about 3D printed drives here. So what's my final verdict? What's better, a 3D printed Harmonic drive or a 3D printed Cycloidal drive? Well, I will give you the most unpopular answer: it depends. I mean, considering the results from these particular drives that I tested, I would pick the Cycloidal drive. It offers greater torque, it's more reliable and more durable. Of course, there's also a room for improving the backlash if we make the cycloidal discs even more precise. On the other hand, the Harmonic drive is definitely better in terms of backlash, but the problem is the flex spline durability. I mean, it handled the NEMA23 stepper loads just like the cycloidal drive, which is fine. However, in order to improve the durability, we would need to use different design of the flex spline, a bigger and longer one, which means that the Harmonic drive would lose some points on compactness. A different 3D printing material would also help. For example, the last flex spline that I made was fine just until the next den when the output started to be even more jerky. I realized that the PLA flex spline had experienced a plastic deformation just by sitting in one position over the night. Let me know what is your experience with Harmonic and cycloidal drives in the comment sections. I hope you enjoyed this video and learned something new. Make sure to subscribe, and for more tutorials and projects, visit howtomechatronics.com.